Hey, welcome. We usually think of sugar as just, well, sugar, simple energy, right? But what if I told you that sugars are actually these incredible, masterfully designed pieces of molecular architecture? Today, we're going to explore the elegant structures that power so much of life.
So let's start with a bit of a riddle. What could table sugar, milk, and insect blood possibly have in common? Sounds kind of random, I know, but the answer? It actually points to this amazing, fundamental principle of biological engineering.
And here is the answer. They all depend on something called disaccharides. All that means is it's a two-part sugar molecule. You take two single sugar units, you link them together with a special chemical connection called an O-Glycosidic bond. And that simple two-part blueprint, that's the whole key.
Now, to really get how this architecture works, we have to zoom way in on one single critical component. We're going to look at what I like to call the anomeric switch. It's a single carbon atom that acts like a master controller, and it pretty much decides the molecule's entire destiny.
You see, in biology, 3D shape is absolutely everything. Our bodies use these things called enzymes to get work done, and enzymes are incredibly picky. It's like a key fitting into a very specific lock. They will only work on a molecule that has the perfect 3D shape. And this precision all comes down to the layout of these things called chiral centers. Where they're placed isn't some minor detail, it's everything.
Okay, so how does this master switch even get made? Well, a sugar like glucose doesn't just hang out as a straight chain. It's kind of floppy, so it folds up on itself to form a much more stable ring. And in the process of closing that ring, boom, it creates a brand new, very special chiral center. And that is the anomeric carbon. This is the spot where all the magic happens.
And this is where that master switch comes in. When two sugars link up, the most important detail is what happens to their anomeric carbons. If one of those anomeric carbons is left free, not tied up in the bond, we call the molecule a reducing sugar. But if the anomeric carbons from both sugars are locked into that bond together, it becomes a non-reducing sugar.
So why on earth does this matter? Well, it boils down to something really simple, actually. A locked anomeric carbon means you've built a super stable, much less reactive molecule. It's like putting a safety cap on it. A free anomeric carbon, though, that leaves the door open for chemical reactions. It's a design choice. Are we building for stability, or are we building for reactivity?
All right, enough with the theory. Let's see this stuff in action. We're going to take a quick tour of 4 really common disaccharides and see exactly how nature uses this anomeric switch to build molecules for very specific jobs.
So here's our cast of characters: Sucrose, Lactose, Maltose, and Trehalose. As you can see, they're all built from slightly different combinations of simple sugars. And most importantly, look at that last column. They have different reducing statuses. That means that anomeric switch is in a different position for each one.
First up, we've got sucrose. You know this one. It's just plain old table sugar. It's made from one glucose and one fructose. Now look really closely at that bond. It connects the anomeric carbon from the glucose to the anomeric carbon from the fructose. Both of those switches are locked down tight.
And that super stable, non-reducing structure, that's not some random accident. It's a brilliant design feature. It makes sucrose the perfect mobile currency for plants. Think about it. A plant makes sugar in its leaves through photosynthesis, but it needs to ship that energy down to the roots or out to the fruit. Sucrose is stable enough to make that whole journey without breaking down or reacting along the way.
Next up, lactose. This is the sugar you find in milk. It's made of a galactose and a glucose. But check out the difference here. That glucose unit has a free anomeric carbon. Its switch is flipped on, which makes lactose a reducing sugar. It's designed to be a readily available, easy-to-access energy source for young mammals.
And in that same vein, you've got maltose, which is made from 2 glucose units stuck together. Just like lactose, it's a reducing sugar. It's got a free anomeric carbon. Now, you don't really find maltose just floating around by itself very often. Instead, it's more of a temporary stepping stone. It's the molecule you get when your body starts to break down those huge energy storage molecules like starch or glycogen.
Okay, our last one, trehalose, is seriously cool. If you look at its structure, it's a lot like sucrose. Both of its anomeric carbons are locked into the bond. This makes it incredibly stable. So stable, in fact, that it's the main energy storage molecule in the blood of insects. And get this, it also acts as a kind of biological antifreeze, protecting them from damage in the cold. How cool is that?
So we've seen the how, right? But there's a huge why question hanging in the air.
Why does life even bother linking sugars together like this? Why not just store a bunch of single glucose units? Well, the answer comes down to solving a universal and potentially deadly problem for every single cell on the planet.
So here it is. If a cell tried to store all of its energy as individual glucose molecules, the sheer number of those little molecules would create a massive water pressure problem. It's called osmolarity. Basically, water would just flood into the cell, and boom, it would literally swell up and explode. By linking sugars together into disaccharides or even bigger chains, the cell dramatically cuts down on the number of individual molecules, keeping that water balance perfectly stable. It's just a totally elegant solution.
So, at the end of the day, it's clear that form dictates function, right down to the position of one single atom. We've seen how nature engineers these sugars for stability, for transport, for quick energy. And it really makes you wonder, right? What other tiny, elegant architectures are out there secretly running the world all around us?